in the... Wait for the... Hello, everybody. We'll just wait for people to sit themselves down. I'm Michelle Doherty. I'm head of department, and I'm very pleased to have you here with us this evening to help us celebrate Yoshi's inaugural. He was promoted to professor in 2018, and his first inaugural date was just after the first lockdown started. And so it's been some time in coming, but we're really very pleased that you're here to help us celebrate tonight. So he studied for his BA in science at Kyoto University in Japan and obtained his PhD degree in experimental particle physics at MIT back in 2001. We were really very fortunate and very pleased when he decided to join us at Imperial in 2004. He came from Stanford University, and he very quickly became a valued colleague in the high energy physics group. He was promoted to reader in 2015 and then to professor in 2018. So we're very proud of Yoshi. He's an outstanding physicist who's worked mainly on the T2K neutrino oscillation experiment, and he's held several high-profile roles in T2K. He also has a major role in the comet lepton flavor experiment. So he was awarded the Fundamental Physics Breakthrough Prize in 2016 for the CAMLAND experiment, and in the same year he received the Fundamental Physics Breakthrough Prize for the T2K experiment. So 2016 was a very good year. Really looking forward to the lecture he's going to give us this evening. He's got a couple of experiments that he's going to run for us as well. But before I hand over to Yoshi, a little bit of housekeeping. There isn't planned that a fire alarm will go off, so if one goes off, it's the real thing. And would you just please follow the people from the department and they'll take you to a safe place. There are people online, and so those people online, if you wish to submit any questions, you can do it during the lecture itself on the side of the screen. The event is being recorded, so if you don't want your name to be read out, you don't have to put it next to it. And of course, those of you in the room, we will have an opportunity to be able to get you to ask questions too. So with that, it gives me great pleasure to hand over to Professor Yoshi Uchida to tell us about exploring beyond the known universe with neutrinos and muons. Go for it.
Thank you very much. Right, thank you very much, Michelle. So, oops. So I'll start with the title. So, Exploring Beyond the Known Universe with Neutrinos and Muons. I know that neutrinos, muons, those aren't part of your everyday vernacular, so I'll try and explain those first, and then go on about the exploring the universe part. So neutrinos and muons, they are what we call fundamental particles, but they're not the most common or well-known fundamental particles. I think the one that is most well-known for everyone is the electron. So I'll start with the electron. It's also a fundamental particle, and that means diving straight into this setup, which I hope will work. So, lights down. This is quite precarious. So now this, if I do this, can you see something? So, I have a backup, don't worry. But there's a blue glow, right. Straight to the backup. You can see the kit, and that's worth it. It genuinely, if the backup works. Right, so this is the video I took of this actual setup in my office. So what's happening here is, well, electrons, they are what flows through wires in a current, and also what orbit atomic nuclei. And so what we've done here is we've got a current going through a wire, And then there, so light comes off like a light bulb, but then the electrons bubble off as well. And I've put about 200 volts on there, and that pulls the electrons out, and they keep on flying. And now I've put a magnetic field. The round thing here is an electromagnet, and so by adding a magnetic field, you can see these electrons going around. So for us, particle physicists, electrons are particles that sort of fly through the air and do things, whereas that's something that I don't think is intuitive normally. So I just wanted to show you that you can just have particles and change the magnetic field. If you increase the energy, the radius goes up. If you increase the magnetic field, it bends back down again. So that's what's going on there. Let's see what the real thing's doing. Yeah, it's frozen. Whoops. Sorry, yep. And so that is the fact that so electrons travel through wires, orbit atomic nuclei, and those are the effects that you just saw there. So this is supposed to be a photograph. I'll go back to the, sorry, electrons, fundamental particles again, rather. And so even though I was speaking about electrons, and that's what was actually going around in a circle, it is photons that you actually saw. So we have photon sensors in our eyes, or in our heads. Those are fundamental particles as well. But there is a difference, and so we separate matter particles. Matter is made up of matter particles. Electrons are one of those, whereas photons are force particles. They transmit forces between these matter particles. And so we make that distinction. And so all of that was happening in here, and I'll switch it off, and then show you the setup that my camera didn't work with. So it's not magic. It didn't work anyway, so... but that's, to remind you, so that is what you almost just saw. And the behavior like this of electrons being particles that you can actually just shoot around was discovered in the late 1800s, and then it was fully understood in the mid-1960s, by which I mean the current full understanding of quantum mechanics, relativity, everything that was going on in here, I think it was happening, it just wasn't seen, was fully understood by the 1960s. Oh, oops. Uh-oh. That is a problem. Right. We'll see. Impressive is the software I use to project the slides. And so, electrons in a magnetic field. I put a little minus next to the E sign, and that's what we are talking about. Now, everything in here I said was understood in the 1960s, so to understand more about the universe, we need to drive it to some sort of extreme. So, one way of driving it to an extreme is maybe crank up the energy. This is only 200 volts, so I can crank it up higher. I can make particles collide. So that's what we try to do, to see things that haven't been seen yet. So here is another ring. It's the same. It's a ring of electrons going around with a magnetic field. There they are, in that direction. And this is where the ring is. So that's Geneva Airport, and ring's going like that. Actually, this one has particles going around the other direction as well, so we collide them there. Up in the top right corner, I lived in a flat there for about 3 or 4 years during my PhD. American PhDs are longer. And that is a very straight road without a single traffic light. And that's the car I bought for £600 and fixed up. But actually, no, the real purpose of that arrow is to say that underground, the L3 experiment was there at the end of that arrow there. So under that ring, there were 4 experiments, L3 with that lovely logo, and I know a few people were with me on that. I was there, and Aleph was actually the experiment that Imperial College was heavily involved in, and was led by Imperial when I was actually working on L3 as a student. So we have an electron beam, positron antimatter electron beam coming the other way. You put the detector in the middle, and then you see something like that. So you can see the shape of the experiment, that octagonal shape. So we sort of cut it across and then see what happens inside. And that blue thing there is an electron. So everything that sort of the light that's emitted in here is sort of captured in there, even though the energies are much higher, and we can identify it as an electron. And then what's this red thing? So that's punching through all the way outside the metal of the red metal there, and that is a muon. So I can bring up muons as our third fundamental particle. They are heavier electrons. That's all they are in our understanding. Nothing else. Heavier electrons. We'll talk about how much heavier in a bit, but the way they were discovered, so particles from space, like the sun or beyond, hit the top of the atmosphere, and then nuclear reactions happen. Now, this purple stuff will denote nuclear reactions, and I'm not going to talk about much, so every time there's purple, just think of that, and I'm not going to say much about it. But anyway, nuclear reactions, muons are created, and they punch through the air and reach us at ground level. Whereas the electrons, the blue things, they fizzle out. You saw how much light they just gave off coming through here. They would just do the same coming down and not make it down. And actually, so this is a setup here that I know isn't working. We tried it, so it's supposed to count the number of muons it can see coming through. If you held your hand out at sea level outside, then you might have a muon go through 1 a second or something. Now, this is under a building, and this detector will say something if it sees a muon going through both of these and count, and it would count quite a slow rate. The problem is I turned it on, it just sort of counts up, so it's not working, but it's an example of a setup where if we saw that, we would say we've seen a muon, and we can count the muons. So when we say we see particles, it can be a very abstract thing, but as long as all the logic is there, we can say we saw a muon. And the experimental setup there, that is the sort of kit we still use in our experiments. So if you want to have a look, please do so. And it's sort of, after all of this, slightly embarrassing to say so, but these pieces of kit come from the first year teaching lab. I think this one was working. And I just wanted to highlight, so the team, I've been in first year lab since 2004, every year. Now I head it. It's been a large part of what I do on the teaching side. And these people, not really the person in the middle, but the four on the side, especially Rob and Harish on the right, they really have been helping me. They really run the labs and keep everything going. And we come in and sort of try to improve things and that sort of thing. But I just can't overstate how valuable this is. So I just wanted to highlight that aspect of, presumably, some aspect of my professorship comes from that as well. So neutrinos. So we are going to neutrinos. Now, you've actually already seen a neutrino. Now, this is in a collider. So we see the electron and the muon. And if you are working on a collider, then you have to think about particles that are invisible, that can't be seen in a collider. That could be a brand new particle that no one's ever thought of. Or it could be something more mundane, but you have to be able to look at that and then take the information there and analyze whether there are any particles that can't be seen. So the way we do that is entirely mathematically analogous to this case here, where we know there's a ball, probably, and then we need to use the information there to devise where the ball is. And my analysis, physicists can all have their own analysis. My analysis would say that that number 2 says that's Joel Ward. Joel Ward always gets stuck in, so the ball must be E. And for copyright reasons, I don't think I should show it, but if you look at the back of this, it does say that that is where the ball is. I don't know what you would have guessed. Probably Kouyate's head. So the exact same thing applies here. So we look at what's happening there. The electron is sort of going that way. The muon's going that way. The particles started out heading towards each other right into that screen. So there can't be a net momentum, energy going that direction. Something has to be going that way. So we know that something was going that way. And yes, we can't actually tell from one case like this. We have to do it thousands of times and then analyze it. But it turns out there are neutrinos going in that direction in there. So it's just that they can't be seen. They're so unlikely to interact that they will just escape the detector without doing anything. I just wanted to show, before I move on, that that was an atypical event. Typically, lots of things are happening, and my colleagues here on their experiment as well were analyzing things. And I'll come back to what was analyzed, but I chose those events because there's an electron and a muon. Otherwise, it sort of looks easier to analyze, probably. And so I'm going to move on. That's the moment I moved on from collider physics. That's when I became a doctor and looking sort of overly proud. Peter Fisher is going to talk to us soon. Professor Becker really taught me so much about hardware. He did pass on lately. And Professor Jeffrey Goldstone, he actually is the architect of a lot of the theory that we're going to talk about later on. So it's a tough day. So neutrinos. A little bit of just information. I can't really do a demo. You wouldn't see the particles. So theorist Pauli 1930, I have done a terrible thing. The experimental evidence made him produce, postulate a particle, but that can't be detected. And he's sort of apologizing for that. Because it only interacts via the weak interaction, we'll come back to that, but these things can be calculated and now measured to travel through light years of matter without interacting, depending on the energy. And every time there's a nuclear reaction, it's likely that a neutrino is produced. And they're observed for the first time more than 20 years later at that nuclear reactor. And they're produced in the sun, exploding stars, and the top of the atmosphere. And now I'm going to talk about the standard model of particle physics. So this is our embodiment of our knowledge. Now, the standard model doesn't sound very impressive, but it really is. And I think the alternative is to have someone's or many people's surnames in a row. So I think standard model is a good name for it. Particles and interactions are listed, perhaps building blocks and rules for them might be a different way of putting it. And they do describe everything that we see at the smallest scales. And if you go to Wikipedia, you see this diagram. I just want you to see that the number of fundamental particles is not that many. It's a lot less than the periodic table. But I just want to sort of tidy that up. I've just taken the same particles and removed some of the information, separated the two because the left particles are matter particles. You can see the electron and muon. And the force particles are on the right. You can see the photon. And what do? Yes, I get rid of names like charm and things because the purple stuff we're not going to talk about. It's confusing, not great names. Actually, I'm just going to call them quarks. So I think quark is a cool name. You've probably heard of quark. So that is what they are, quarks. They're laid out so that the particles tend to be heavier as you go to the right and upwards, roughly. But the neutrinos have absolutely zero mass in the standard model. Now, the Higgs colleagues discovered a few years ago, but we're not really going to talk about that, so bye-bye. And the gluon is a force particle for the quark, so it's called a gluon, so I'll just sort of use that color there. And the photon is what mediates the electricity, light, and magnetism that was happening in there. And then this Z and W, this is the weak interaction force particles, and those were studied in extreme detail by the experiments, the 4 experiments. So I've put that one there, but they all did that. They produced many, many of these and really studied them to test the standard model. So the weak force, radioactivity, that sort of thing, uses those particles. And then the photon connects to the quarks and the electrons and muons, but not the neutrinos, as we said. And then the weak force connects to all of them. It gets a bit busy, so let's move on. Now, this part of the model is the Glashow-Salam-Weinberg model, but they actually unified it sort of mathematically. The main reason I'm highlighting that is because Salam was here when this was done, and you can go upstairs and look at the wall there to see the Nobel Prize that he won, or that Nobel Prize actually. That's what he did. So now I'm going to talk about the interactions of those particles. So these are the rules. So the electron can go along and feel a photon, like it was doing there, to be bent by the magnetic field, and so can a muon. They're the same thing, really. They're just, the muon is a heavier version. The electron feels the weak force, and so does the electron neutrino. So the Z feels both the same way, but, well, the neutrino doesn't feel the photon, and the W is a bit special, that it can take an electron and turn it into an electron neutrino. And that's it. These are the only things that an electron or muon can do. So it's actually not that many. These are all backed up by numbers and calculations in the theory, but the basic way that you can write them is as these. So everything that you can think of that these particles do, you have to use these combinations. And bring in the quarks and things if you need to. So that diagram there, all of those steps are actually following that. because there's no new stuff in there. We've learnt it and we've applied it. There are Z's and W's that aren't shown there, but they are implied and they follow all the rules. So all that a muon can do on its own, if you have a muon, other than just staying a muon, is to do this thing and turn into a muon neutrino. That's all it can do. And then that W, all that can really do is go into an electron or electron neutrino. If it went into a muon, the muon will be producing loads of neutrinos, and that wouldn't work. So that is all that happens. And they all do that. So a muon, if you have it, goes through that and turns into an electron with neutrinos, 2 neutrinos, leaving it. And that's why that takes about a millionth of a second for all of them, roughly, on average. That's why muons don't last. They die after about a microsecond. That's why we don't have currents of muons going through wires, or we don't have atoms with muons going around them. We do with electrons. That's the main difference. That's why you haven't really heard of the muon, because they just disappear. In everyday life, they're not that useful in everyday life. What an electron can do, it can't do that. It can't turn into a muon because the muon's so much heavier, need much energy, much more energy. So an electron just stays that way forever. And the particle physicists in here who are nitpicking, you can see I put the do in italics, so it's a very specific do I'm talking about. But I think this is all true. Bit wordy, but probably better than equations. So standard model, small number of fundamental assumptions about the universe that led to relativity and quantum mechanics and things, and choices based on observation, and it's predicted everything. But we know that it can't be complete. There's no gravity, dark matter, why the universe is made of matter. These questions can't be answered. So at the small scale, it's almost perfect, but at the big scale, it is lacking. And therefore, we particle physicists, so much of what we do is to search for physics beyond the standard model. We call it BSM. Everything, almost everything is a search for physics beyond the standard model. And so I'm going to talk about one experiment that has looked for science beyond the standard model. This is Super Kamiokande. It is reasonably something that is sometimes seen in the popular press. It gets filled with water, maintained by, it turns out, 2 imperial people. One of them is here, Arthur, is sitting there. You can't tell who he is there, but it is. That is Arthur there. So that can detect neutrinos. And so here, you can see at the top of that globe there, Japan is at the top there, where Super Kamiokande is, and it's not to scale. It's a huge detector, but it is a bit smaller than that. But the main thing to see from there, it's the top of the sky thing producing neutrinos. So if a neutrino is seen from above, it's only traveled about 10 miles, the thickness of the atmosphere, since it was produced. Whereas if one comes from below, remember it can just pass through anything, so it'll pass through the Earth, you can actually see the neutrinos coming from below, then it must have traveled something like 10,000 miles, sort of the radius of the Earth, to get there. So you can just look up and down. This is a seminal talk from 1998, and in those days, that's how people gave talks. I'm going to sort of reduce some of the information. You're comparing data with predictions, and the main thing is there, the data, the crosses at the bottom, are lower than the gray regions which were predicted. Everywhere else it matches. So what this is saying, that muons that are going up, if you can see the top, those are the ones that are going up. Those are the ones that have traveled a long distance, are acting differently to the ones that came down. And just from that, we can state absolutely that neutrinos are not massless, have weight. This is the Einstein relativity issues, that if something has no weight, it can go at the speed of light, or it does go at the speed of light. If it goes at the speed of light, time freezes for it. It will go, as it goes past, it will look like a stopped clock. This is the sort of thing that we take for granted. Relativity is absolute bread and butter. It's absolute fact for us. I'd like to dwell on it and talk about it, but what you can do, if you're not acquainted with that argument at the bottom there, ask any physicist hopefully from the first year and above, I think, and they can explain it to you. So I have to move on, but it is really exciting, just an observation, to think that tells us that. So now we know that neutrinos are not massless. That is a fundamental part of the standard model in the way it was written down. So they're massive. and I say they have no size. So massive means with weight, not massive, as we use it. So massive neutrinos, weigh more than 0. So does that mean we can just weigh each one? Electron neutrino, male neutrino, and the third one I haven't really used a name of, but it's a tau neutrino. And we're finished. 3 experiments, it'll be very difficult, but no. Actually, if you have 3 a light, medium, and heavy neutrino, and you've got the electron, muon, tau neutrino, the combination can be like this. There's no reason why they should match. Why should the electron be a light neutrino? That means that you suddenly have all these numbers to measure. And that means an experiment needs to be there to measure it. So I've been avoiding maths until now, but this bit here, and I know some people here would probably be choosing how much maths to do in the future in terms of GCSE or A-levels and things. So I just wanted to say that something like this, even though it's so fundamental, you need things like matrices, and these numbers could be complex. And so for this sort of thing, maths is valuable as well. Rishi Sunak will agree, I'm sure. So that was Super Kamiokande. Now we sort of know that neutrinos have mass. So at Stanford, I worked on this experiment called CamLand. Now this is a talk I gave in 2003. It was a big deal as a Stanford colloquium. It was a new result. I spent about 45 minutes getting to the result and then another 15 digesting it with the audience. But I think I'm doing it in about 3 slides. So it's 20 years ago. So that is the largest nuclear power station complex in the world. Kashiwazaki Kariwa. I could say it better, but it's a bit embarrassing to do that. That's our experiment, CamLand, and they're separated by about 100 miles. And that's actually the symbol for electron and neutrino, neutrinos that come from reactors. So this is just a scene of the experiment being built. It's a bit like the Super Kamiokande. When you're looking at light, you have all these bulbous things that look for light. And this was complete by early 2002 and ran for 145 days. And the reactor's 100 miles away, and you can calculate by receiving faxes from the power station saying how much power they produced that day, and calculate the number of neutrinos in 145 days. That tank, that's actually about 13 meters wide, so it's sort of this size, is the size of this room, should see. With error bars, students, always error bars, errors on the numbers. So if all the neutrinos came from the reactors without loss, we'd see 87, plus or minus a bit, and we saw 54. So this is the first time, having been discovered at a reactor, that anyone saw these disappear. And that can happen if they have mass. It's quantum mechanics. So this is the breakthrough prize. I've got the certificate, but not the medal. Maybe someone will hear this. And so all these other experiments, the first Savannah River one is up there, slightly high, but this is the comparison between how many you think would come if they all came to your detector, and CamLand is out there, and it's much smaller than 1. So that itself is a big discovery. I just want to get across this feeling of discovery that when we build these experiments, we don't know what the answer is going to be. We say, let's build an experiment where, if something is going on with Mother Nature, something might happen, but we build it, we turn it on, and so often what we get is sort of mundane, standard model or that sort of result. That's still valuable, but that feeling of turning on a detector, we've set it up, and then you get less than 1 neutrino every day, and they're sort of just piling up. You're not really watching as they pile it up, but then you look at the end, and suddenly you've got a lot fewer than you expected. That feeling is real discovery, really communicating with the universe as it tells us what it's about. After that, it actually also measured, the experiment measured the neutrinos coming from the Earth, which has nothing to do with the rest of the story, but it was on the cover of Nature, so I do need to show that off before I move on. Now, T to K, as Michelle said, this has been a huge part of what we've done here at Imperial. We have a few colleagues who have been working on this. This is an experiment that takes actually Super Kamiokandes at the top there, makes a beam of neutrinos and sends it from Tokai. Going to do something slightly unconventional, because in talks like this, we sort of say, we set up an experiment, and it was built, we turned it on, we got these results, and this is the number or plot, just like I showed you, that sort of thing. But I think many people will be wondering, what do you actually do every day? So I don't just sort of sit there waiting, having built a detector and wait 145 days doing nothing. We are doing things. So just a taste of that. I can't go into too much detail, but anyway, the beam cuts across Japan, so it goes slightly underground and then comes out the other end where that experiment already was. So this is the experiment that was very exciting for us, and it's a time when I came here. So a slightly personal story. So there I was in California with my car. Oh, if you insist, yes, it's that. It's like. So I was reluctant to leave. That was nice. The weather's nice as well. Maybe not that day. But, and then I saw this thing in CERN, Korea. Imperial College is asking for a professor and a lecturer. So I didn't get the lectureship then. The professorship then. I got the lectureship. So having thought, yes, well, that car's nice, but in London I didn't need a car, so I left it there. And I arrived here as one of the two people there. And then we as in a group of people, spent 2 years writing this proposal for T2K in the UK. It's a very international, I think it's 12 nations at the time, but we played a pretty big role. So we would speak with other physicists and engineers across the UK institutions, and of course go abroad and talk to other people. All these things have to come together. Initially brainstorming in front of a blackboard or whiteboard, detector ideas, and then go back and run a simulation, and then talk to engineers about how feasible something is, just back of the envelope designs and things, technicians, how much would it cost roughly. And our two PhD students at the time, they did a lot of the actual work, always. I think the word PhD students will appear a lot, and that's because we do love them so much. So Imperial, in that case, we took on, I led the physics and software, and we needed to develop new photosensors as an experiment. The electronics were designed here. I know some people have come back from retirement for this here, on the electronic side, and things like management. Physicists manage stuff, even if we're not very good at it. And we submitted in January 2006, and then reasonably soon, it was in a year, it was approved. So we started building things, but it wasn't actually fully approved. So we started building things with the money we sort of had, and I became software convener from that role. And we're working with third year and fourth year students as well. That's the group at the time. Morgan joined by then, you can see. And then the proposal was fully approved in September 2008. And then we were told, we actually have approved you, so actually you can carry on building what you've already started building. And so we carried on. So we built it across those institutions. It's a very tightly knit group. You can imagine how intense this sort of period is. We really would go to each other's universities. A lot of it was Warwick, actually, but we would all meet at Warwick and then go to each other's universities, national labs, and devise how to build things, how to test things, how to assure the quality of things, and hire people and do things ourselves. There are some really meticulous tasks which people here in the group are amazing at, and you wouldn't want me to do that. And all of these things work together. And now we knew that we were going to be doing the experiment. We had to really start getting prepped on the plans for data taking and physics analysis. You can imagine software plays a large role in that. Data processing, I had to do that a bit at the last minute. Some people will remember me panicking about that. And then the first detector module was ready for testing in 2009. So you can see up there at CERN, test beam data taking at CERN. You can see actually a few people here. And I would say an experiment like this is about discovery. And I'd say the biggest discovery ever was on T2K, and that was before we finished building it. It's in the photograph, and she's sitting there as well. So you can talk to her afterwards, so we won't dwell on that. So now it has got personal, right? You're thinking, that's not very personal, this story. It's just sort of an academic life, but that bit is quite personal. So by that time, we had about 4 students after that, and then we really went to Japan, installed, commissioned the detector. So the students were out there for a long time, a year or more at a time. I went there as well. Really working many, many hours a day to get this thing. And all of these people from 12 different countries are there, as well as the host nation, Japanese people. And then by that time, we had about individually a PhD student every year because there was so much to do, and we had the BSc and MSci students helping out. And with all the systems all delivered, mostly 2010, we really did start taking data. Now, I made this picture, and that is still being used. It's probably the actual contribution to TTK that I made that upstairs one evening that is actually being used, probably has been used more than anything else. I'm being modest here, but... And then once we had the detector going, neutrinos would come and make these interactions. It's a bit like what I showed in the collider, but energies are lower and the detectors are very different. Neutrinos are going through the whole thing, so we don't know where the particles are coming from. We are actually excited about this interaction here. So a student of mine, Ben Smith, found this. That is a neutrino in our bit of the detector that made a little signal. So, as I said, I'm skipping the sort of usual part of it. I think I have to do that. But so 2011, we came up with this result. So this is sending these neutrinos to the other side. They're actually muon neutrinos, but we're counting electron neutrinos there. And we saw 6. If you count the 2, 2, 1, 1, that's 6. And then the colored bands are our estimation of other things that aren't interesting, that look like the neutrinos that we're looking for. And so these are signs of muon neutrinos appearing as electron neutrinos after traveling this distance at a particular energy. And that was also a first time. So we didn't know if this was going to happen. This number could have been literally 1,000 times smaller instead of 6. So it would have taken 1,000 times more time to get to 6. But it happened to be quite large, and so that's the other breakthrough prize I didn't get a medal for. And jumping ahead, we carry on running, and now we reported, again, so this is an Imperial contributed result on the Curve of Nature, so this is more justified. But TTK, we reported signs of a difference between matter and antimatter neutrinos. So we would send matter neutrinos and antimatter neutrinos and look at the difference, and there seems to be one. That actually is a complex number, the i's that squares to a -1. That's what we're measuring, and it seems we are sort of onto the possibility of there being a complex number in there. We did a Reddit Ask Me Anything at the time. This was just into lockdown. So just about when I was supposed to be doing this, I suppose. But you can actually go there and look at our conversations if yes, I suppose that'll replace what I could have said here about this. But we do need to talk about muons. So, and I think that's the most recent Imperial group photo. Everyone's looking pretty happy. Neither me nor my friend and colleague Morgan are there, maybe that's why. But we have a few younger academics that you can hardly tell from the undergrads who are there. I want to mention one specific thing. So neutrino-nucleus interaction modeling. A nucleus, an atomic nucleus, the things that the electrons are going around, doesn't really look like that, but it's a complicated object, and it's made of the purple stuff, quarks and stuff, messy things. I actually tried to get an AI to make a better version of this, but no, they look like chandeliers or something, useless. And so if you come along with a neutrino, which has a very specific way of interacting, and it can just sort of bury inside and interact inside there and everything, it gets excited, and all these crazy things happen, and I wasn't going to draw that. So you can imagine lots of crazy things happen. It's really difficult to model. And for people like us, it's just really difficult. But we are very fortunate and honored to have someone with a research fellowship, 1851. So that comes from the Crystal Palace. That's not a gratuitous mention of Crystal Palace. But she has this fellowship. I thought I'd use this photograph when we were videoing to my student together, but I think she probably prefers this one. She was invited to number 10 recently, and I think that's a nice, impressive photo. She's right there, so you can go and talk to her. That's Minu. And she writes these single author papers that really are theoretically rigorous with proper approximations, and she's now with us going to be able to incorporate things like modern computing techniques, statistics, and quantum computing possibly to really try and do the best job that can be done as a fellow. And it's just amazing. It's such an exciting part of what I'm associated with. Now, so beyond the standard model, neutrinos are not massless, and that's a huge program of discovery is underway now. There are so many things to measure, but anything else, there's another side. We want to see other types of physics beyond the standard model because neutrinos won't solve all those issues. So a muon going into an electron and something else coming out. So that can't happen, right? We said in the standard model there is no such thing. A muon can't just go into an electron. It's always the muon going to a muon neutrino. So this can't happen in the standard model. And so that's banned in the standard model. And I found myself trying to turn this into some Ghostbusters sort of logo, and I realized, no, I shouldn't be doing this. Don't waste time. But that's why we're searching for it. So if you can find something that is beyond the standard model, can't happen, but with small tweaks of the standard model just about can happen, then that's an interesting thing to look for. And so a muon going into an electron like this, without neutrinos going out, is, we feel, worth searching for, and I bet we'd get a breakthrough prize. That's their logo, if we found that. And so the experiment is called COMET, the Coherent Muon to Electron Transition Search Experiment. And several of us here, thank you for coming from abroad as well. Whereas my neutrino colleagues, half were in Fermilab and half were in CERN. And so the neutrino world has not come to a standstill for my inaugural. Well, it's not as if the muon world has either, but, well, let's carry on with muons anyway. So this is the setup for the COMET experiment. About half of it would fit in this sort of footprint of this room, perhaps. I'll explain how it works. So you send a beam of protons into a bit of matter right there. What that is, it's exactly the same as beam of protons coming from the sun hitting the top of the atmosphere. It doesn't matter where it hits. It does the same thing, produces muons and neutrinos and things. And in this case, instead of coming from the sky, the protons whirl around there. I should have sort of made an animation or something, but it's cheesy. At the end of the accelerator, it sort of pops through, comes out, and the protons come and enter that building there underground. That's where the COMET experiment is. So proton beam arrives, all the stuff happens, you can see some purple there, but all of this is a system of high-field superconducting magnets. So imagine this. This is about 1 millitesla, and that's about 5 Tesla. So you're talking a factor 1,000 sort of level difference. So it's just like this. Particles will start going around in a circle or a spiral shape, and we do that, but it's much more powerful. We have those companies that are based there that can make these things. This is cut halfway through, by the way. Perhaps I do need to mention that. It's actually a pipe-like thing normally. And so the particles will start spiraling down there, turning into muons, the red things, as they spiral, just like in the sky. And by here, we can make it so that about 1 million muons arrive every 1 million times a second. So every millionth of a second, we have about 1 million muons come there. And we have some matter there. It's actually some thin sheets of aluminium. So what happens is the muons come along, and they start orbiting the aluminium. So when earlier I said, well, you don't get muons orbiting atomic nuclei, I was going to say, or do they? But my acting skills, I thought, no, let's skip that. But so they do that, and they stay that way for about 1 millionth of a second. And so I'll say and so then we can see that, sorry. We can observe them. I just want to put this in context. So this has been designed over many years. We've been working on it a long time, similarly to what I said before about the process of doing these things. So phase alpha is a commissioning run. That was in March. So that's at that time. And so Ollie and Kevin went there. They designed and built this contraption that helps us understand the beam. There's a hole you can see, and that moves around. I was there as well to take photographs. And so that's a setup. And actually, so if the beam comes that I showed with the purple arrow comes through from the right, and then it bounces back, and then it goes through the white thing on the top left. And on the other side of that, you can see on the left photograph at the top right, there's the other end of that. That's a superconducting solenoid. this is a case where I was showing around the Minister for Science and a representative of the Department for Science at the time, so that's also gratuitous. I just thought I might put that there. Actually, on the right, this is the Imperial and, or the UK and Malaysia comet groups. We work together with other nations as well. So this was the first time this Beaman had ever been turned on. So it was a big deal, and we did see data, and we are working on it. And so that is a commissioning run. And so the experiment is going to go into phase 1, which is in a year or so's time. And you can see that it doesn't have the full long shape, snake-like shape, but it's only the first part. But even then, there are lots of muons being produced. Still a few more pions. Sorry, I haven't mentioned pions so much. Other stuff. And so we're building this thing, and this is all coming along. I just sort of have representations of software and things that is so important behind the scenes that might not be obvious. Preparing analyses and things. So, muon to electron conversion, this thing where a muon goes into an electron. So muons are heavy electrons. Now, E equals mc squared is this equation, but it's actually just telling us that energy and mass are equivalent. So if you have something that weighs a bit, that is equivalent to energy. That's Einstein as well. And so what's happening is, so if this were an electron, so it's a light particle, and this is a little ping-pong ball, I think you can sort of sense how light it is, then a muon would be the weight of, and I want you to think I still have a red ball, but I'm afraid it's red and blue. But this is just about the proportion of the weight of an electron to a muon. So you can sort of have a feel for that. Now, they both have no size, so the size is irrelevant, but I think that's the intuition for it. And what happens when a muon turns into an electron? So you have a muon, and through some magical beyond the standard model process, it turns into an electron. But this mass energy has to go somewhere. So what happens is that this will have to go away to my wife. But all of this mass energy goes into that, and it's a very specific energy that goes into it. So every time it's going to be the same energy, and that is a signal. So the energy we're talking about, if you actually calculate, so this was 200 volts on the electron. So you saw the sort of energy, you could feel how they were going around in a circle. This energy that the electron is supposed to have, a real electron, would be 1,000,000 times that. It's 100 million volts equivalent. So if I crank this up from 200 volts to 100 million volts, then those electrons would be going at about the right energy that a real electron would from a muon. Now, if I converted this energy to, well, sorry, this mass energy, that would be the energy of a nuclear bomb. So this is an analogy. Muon, electron, specific energy. So what happens is that a lot of messy stuff happens, but you have an electron going around in a circle in a magnetic field at in a very specific shape because it has a known energy. And remember, by increasing the energy, I could change the radius here. The same thing happens. And that orange thing there, if we saw it in the mess of things, within the microsecond that we have, a millionth of a second that we have, that is allowed for a muon to live, to do this conversion thing, then we would have a discovery. And that would be, hopefully, the breakthrough prize. Now. So that's what you just saw. But this is a animation a different student, Matthias, made of what would happen over a millionth of a second. So this is happening over a millionth of a second. All sorts of stuff happens. We wait. It gets quiet because now we are getting things from the muons. And that was that specific electron. So what we would be doing in this detector, running this over and over, just trying to make as many of these muonic atoms as possible, these muons just orbiting around a nucleus. And if some beyond the standard model stuff happens, that muon turns into an electron, suddenly that energy will be acquired and it will pop out and do that. Shall I see if I can get it going again? No. Right. So that's what we're looking for. working with young people is one of the delights, and I have another one to introduce here. This is Oishi. He's also here. So I put Comet, well, he's leading Comet Phase Alpha. He really designed Phase Alpha, that setup and everything, and negotiated, represented the collaboration with the lab, gave us beam time. But then he's also leading a lot of Phase 1, which is coming, and then his PhD thesis was on Phase 2 studies before he came here. So I just thought, well, actually, he's doing Phase Alpha 1 and 2. And so there's Ko for you. He is a Marie Skłodowska-Curie individual fellow. So those are the two fellows I have the honor to work with. So as we wrap up, so COMET, it is a search for muon to electron conversion in the vicinity of a nucleus. We did the commissioning tests earlier this year, and so we're really excited about that. It has taken a long time to get here. And in the next couple of years, we want to get 100 times better than the current limit. And then Phase 2, following that, learning from Phase Alpha and Phase 1, we want to go to 100,000 times better than the current limit. By that time, we're talking about looking at 10 to the 18 or 19, so a million or more muons, watching them and seeing if just a handful actually do that specific circular motion. And then we have to prove that we've seen what we think we've seen. That's the future for us on the muon side. I do need to mention, so TTK is still going strong, and we are running. We're running again very shortly, but our group is involved in 2 future bigger experiments, one at Fermilab, so this is going across America, based in the northern part of America from Chicago with a very powerful beamline, and Hyper-Kamiokande is near Super-Kamiokande. It's 10 times bigger than the Super-Kamiokande that you saw. In a diagram like this, you can't really tell the difference. It can't tell that it's so much bigger, but it definitely is. The neutrino beam is going to be made more powerful. And once you have something like this, you can also do neutrino astronomy and all sorts of other physics with it as well. So we have, both these experiments have significant UK and Imperial participation, and that is the future. Towards the end of the 2020s, many of us working here will be working on this as well. This is the status. So about just under a year ago, that very top bit of that huge cavern was excavated, and things are moving forward really rapidly. So the standard model is really good at describing the universe at the smallest scales, but it's not complete, so we need to look beyond it. Neutrinos have mass. We absolutely know that, and now we have a whole range of different measurements that we're making, and Dune and Hyper-K will make a range as well, but other experiments, we're all competing and working together, and that's opened up. And one of the big things is that that could actually possibly lead to us understanding why there's matter but no antimatter around in the universe. But we need to go beyond the standard model in a different way as well. Just studying neutrinos can't be everything. So from someone like me, having a smaller experiment, it definitely is smaller, and more nimble perhaps, to look for something like muon to electron conversion, casting a wide net, so that so many different theories, we're not saying we need to pinpoint this theory and do an experiment to test it. We're saying this is a process that if the standard model is slightly different from real, or nature is slightly different, this is somewhere where it could pop up, and we're going to just try and push that as much as we can, orders of magnitude. So that's what we're doing. But that's the main message. Both neutrinos and muons, by allowing us to understand the universe at the smallest scales, mean that that can also be projected to exploring the universe at the greater scales. I'll just finish with a few photographs around the world. We collaborate a lot. I think so much of what we do, even though it's the technical things that you will be interested in and that you ask about, but it's the people you meet, we meet, as we do this from around the world, different cultures and languages, different physics, sort of science cultures, but there's only one physics, so we all actually come together, and it's such an amazing thing. So I just chose a few photographs where that might be representative. Thank you very much.
Thank you so much, Yoshi. So, questions from people. I know we're going to have some online questions and we're going to jump between the two, but who's brave enough to ask the first question? Please. We've got mics so that we can hear the question.
Thank you for the talk. It was a really interesting subject that you are researching. I'd like to ask you, as you research further into subatomic particles and look for unknown particles, are you coming to understand the nature of space itself? Because we think of it as the void or vacuum or sheer emptiness, but the old Newtonian idea of luminiferous ether sometimes keeps reappearing, that space itself may be a medium. So my question really boils down to, is space something or nothing?
I'm not sure I can answer the specifics, but if I take the way we think about it now, the fundamental particles I put up there, and also the interactions that they have, those are set out, and then anything that satisfies those can happen, and that does include, from the vacuum, particles just bubbling up for a fraction of a second and going away, and that is in the theory, and you try and include it in that so that it sort of defines the vacuum, but people do make measurements of what's happening at the tiny scales that may be exploring what you're saying. What I'm saying, what we're looking at is probing what those particles are and the rules are. There might be deviations, there might be other particles, other force particles that maybe turn a muon into an electron. So we're trying to find those rules. With those measurements, you can project into the properties of space, and there are physicists who focus on that as well. I don't think I can say much more because we are focusing on the structure that the universe seems to have. We're probing it and we're trying to understand it as a model in a reduced way that we think explains things.
Thank you. Is there a question online, Roden?
Yeah. Is this working? It is. So one of our questions is, if neutrinos have a different mass and they can change identities, does that mean if a neutrino changes to a lighter type, it goes faster? And if so, does that change the internal relativistic neutrino clock of an experiment?
So the fact that neutrinos, quantum particles that are described by quantum waves, and it is everything, but with the neutrinos, with very, sorry, yeah, looking at you for some reason, but yeah. Don't know who to look at. But where was I?
You got yourself very distracted.
I know. I looked at Roden's eyes.
Roden, just
oh yes.
Just nod.
Yes. So very, very. So the specific case of no charge and very, very similar masses makes them where all that uncertainty will go when you've got a setup. But at that point, if you're talking about energies and masses and things, they aren't sort of like billiard balls with specific masses traveling and suddenly turning into a different type of billiard ball. They are probabilities, waves that are interfering. So it's sort of yes and sort of no, but you have to write it down in the maths, and that is what it actually is. I don't think it's an intuitive, that's what it's doing, is probably the right way to say it.
We've got well, do you want to, there's a lady just behind you, just so that you don't have to walk up and down the stairs 100 times.
I have a very practical question. How do you detect those particles? Is it the same idea that a photodetector, or is it more complicated? And I guess a related question is, how do you know which particle you detect?
So I did have to skip some of the things there. So if a muon neutrino comes in, perhaps, if I pop to the interactions slide. So if a muon neutrino comes in, you can see these are the things that it has open to it. And so it's the left, say it's the bottom two we've got. It can either undergo an interaction where it stays a muon neutrino, so it might very, very gently affect the material but carry on as a muon neutrino that you can't see, or these can go in different directions. It's just an example. So you can have a muon neutrino going in and turning into a muon if it has enough energy, which isn't that much. So what you would have is, in the middle of your matter, a neutrino coming in that you can't see, and then it does that, and a muon suddenly appears, and then that W goes and also interacts with something else it can interact with. That could be an electron, but it's more likely to be a nucleus. So we said that so the nucleus is made of quarks, which I didn't talk about, but that's what protons and neutrons are made of. And so the weak force is there, that W we had can interact with those. So that's what's typically happening. And so in your detector, you would see a muon, if it's a muon neutrino, a muon come out, and then possibly some other things like a proton emerging as well. And so you just need a large amount of mass, or matter. The neutrinos, the more there is, the heavier it is, the more likely the neutrinos will interact. It's still at 1 in a trillion for the sort of experimental engines we're talking about. So a trillion neutrinos come through, one of them does that, and then you capture what comes out of there. And then we have the means to identify muons. There's lots of ways we design detectors so that we can try and accept muons no matter which way they go in, that sort of thing. So you end up with a transparent thing with looking for light in all directions is what you often end up with. But there are many ways. So you're just looking for a particle that's easy to see to suddenly pop up in the middle of nowhere.
So I know I have two questions here. I haven't forgotten you. I'm just going to go online if there is one.
Yeah, there is a slightly edited one. So what tweak to the standard model facilitates the query of muon to electron conversion, and how different are the BSM alternatives that we'd need?
So for example, I haven't brought the diagrams for this talk, but you can have a case where, so I'll just go to the standard model ones that we have. The beauty of it is that we don't have to worry about it. That's not the particles. And so we could tweak this in any of these. The Z could be something else, and we can have, and literally there are things like called a Z prime, Z with a dash on it, that just behaves a little differently and then possibly occasionally links a muon to an electron. There are, and also supersymmetric particles, that's a popular theory. It's actually quite, because you're adding particles, potentially matter particles that these can go on and come back to, or new force particles. So actually, unless you often constrain it so that muons don't convert into electrons, then it can often happen. So we are casting a wide net. There is you can have sort of tabulated lists of models that do that, but, well, I don't right now have a list that I could show, and it's not really the purpose. We're choosing something where a small tweak. So for example, neutrinos are massive, but they are very, very light. So experimentally, they look like they were zero for so many decades. But imagine if the neutrinos had a large difference in mass. Then it would be much easier for muons to turn into this thing to happen, muons to turn into electrons. So beyond the standard model of physics, neutrinos, they happen to have mass. They are very, very light, and so that number is very unlikely. The number I like to sort of throw about is that, so with the specific way that we now know neutrinos can change from a muon neutrino to an electron, that is beyond the standard model of physics. If you take that and apply it to the muon and wait for it to turn into an electron, then you need 1 with 54 zeros after it. So not even a billion, million or anything. It's 54. And if you actually produce that many muons, like we are trying to produce lots of muons, if you made 10 to the 54 muons to see that, those would weigh more than about 30 times the mass of the Earth. So it's not it's just around the corner. If we work 10 years from now, we might be able to probe that by making lots of muons. No, we'd actually have to start taking solar systems and turning them into muons and sort of observing those. So that's, no, not for my generation of experiment, I think.
So we're going to take 2 more questions. We've got the gentleman with the red shirt and then the young gentleman with the cream shirt.
Thanks. Yeah, I hope this is not too imbecile sounding a question, but you mentioned at one point measuring a complex number, so obviously you're trying to say something else. I was just wondering what you were using a shorthand. I appreciate you've got to get through a lot of stuff. So what do you mean by that?
Yeah. Right, so I don't have the matrix. So this is all quantum mechanical. So each of these are representing, even though so the notation is sort of obviously, well, simplified just to get the gist of it, but both the things at the right and the things at the left, they're quantum mechanical entities. So if you multiply it by something, you can multiply it by I. So that's a matrix with complex numbers. And so it could be that they're all real. It could be that there's something complex in there. And if you actually take the possibility of there being a complex number, an I somewhere in there, then it turns into the difference between neutrinos and antineutrinos. And so you can constrain that by doing an experiment with neutrinos and doing it with antineutrinos and looking for the difference, which is what that Nature paper for T2K did.
Okay, we're going to have one final question from the front here.
With what you said about muon to electron conversion, going beyond the standard model, I would guess there would be like many different ways different conversions that would go beyond the standard model. What is it specifically about muon to electron conversion that's led you to do all
Why muon to electron convergence? So first of all, we have electron, muon, the tau, which I didn't mention much, but there is that third. All of those particles, there are 3 of them, and that's one of the mysteries. And so tau is going into mu's in the same way, or tau is going into e's, is a possibility, and we should look at them. Experimentally, we can make just about 10 to the 8 in a million muons and watch them. Taus, they live even shorter, so it's experimentally really difficult. You would actually have to see it at a collision in a collider and deduce what's going on. And that is looked at, but the numbers aren't going to, you're not going to get the same numbers. So definitely you can write theories where that sort of beyond the standard model stuff happens between muons and taus, but not between muons and electrons, maybe. You can write them that way, so even though we cast a wide net, it's not something that magically covers everything, but it's a combination of experimentally what's an area we can push by orders of magnitude, and are those orders of magnitude interesting, that is just as much important. So the answer to the question is no, there isn't necessarily any reason, but experimentally there is a good reason to look at this.
Okay, Yoshi, thank you. And I'm sure if there are more questions, people can come and talk to you afterwards.
Yeah.
Cool. Okay, so we're going to move to the last part of the formal session now, and we're going to hand over to Peter Fisher, who is going to give the vote of thanks. I think we need... Oh, there you are, Peter. Hello. So Yoshi was a PhD student of Peter's, working at the LEP Collider at CERN, and Peter's always been a valued advisor and mentor to Yoshi. So, Peter, may I hand over to you?
Well, thank you very much for doing this, and I wish I were there. I can only say I'm not really out of the pandemic yet, and couldn't come. But first of all, I want to thank Yoshi for a terrific talk. It's really just excellent to see someone who's so good at public communication and who's done so much and can talk about it in such a simple and clear way. As a footnote, when I first met Yoshi, I called him Yoshi. He, I think, a few times reminded me that it's actually Yoshi, but never got there, and now it's too late. I'm getting a little feedback from my talking, but I'll push on. I'll give you a little context about myself. I started in neutrino physics in 1983. And in 1983, that was the year that the W and Z particles that Yoshi mentioned in his talk were discovered. And that really put big collider experiments on the map. And all my friends were working on these huge things with all this high-tech stuff and computers, and which were kind of a new thing then. And I, for some reason, went to work on nuclear physics and actually did an experiment, which I'll mention later, very similar to the Camland experiment Yoshi mentioned. And part of the reason I stuck with the group was my advisor, who I'm showing a picture of. That's Felix Bohm. And so Yoshi, that's your academic grandfather, right? Felix is a Swiss and just a wonderful man, had many, many ideas. And, but at the time, neutrino physics was really, I'm not going to say disreputable, but clearly second tier, and a lot of people didn't take it seriously, and it was all about these huge experiments. And I've kind of had the privilege of, since then, not being in the field, but seeing the field of neutrino physics in the hands of Yoshi and his cohort really assume its rightful place as a precision field. The progress in the 25 years or 30 years since then has really been terrific. And I'll mention there's still a last great measurement about neutrinos, and that's whether the neutrino is a Majorana or Dirac particle, whether it's its own antiparticle or not. So since then, I've been involved in since getting my PhD in 1988, I've been involved in some mildly disreputable things, the L3 experiment, the alpha magnetic spectrometer, a terrific experiment called the dark matter time projection chamber. And I hope Jocelyn and Asher are there. That was a real privilege to work on. Primordial black holes. And then I served as physics department head at MIT for 9 years, and throughout have been periodically doing weird things for the government. And through that time, I've worked with some really terrific people, and Yoshi, who I'll go on and on about, is a high point in that. I want to make the case, particularly for the young people, it's not really bad to work a little bit with bad people. You learn a lot, they test you, they push you, you learn how to get away from them. So, make it a point to work with some, bad people. But anyway, back to the good people. Yoshi showed up at MIT in the mid 90s, 95, I guess. And right away distinguished himself. I meet with students weekly, and I asked Yoshi how he was doing with his graduate exams. At the time, it took students 2 or 3 years to get through them, and Yoshi just said, "Well, I've done them." And I said, "Oh, you passed both on your first attempt?" And he said, "Well, yes. I went to school in England, or I went to school in Japan. I was prepared." So right away he set about working with us in building 44, building gas detectors, and really demonstrating a lot of passion for making things. We worked with Ulrich Becker, and here's a picture of Ulrich there. This was taken in building 44, so you can see what a dump it was. And I think there was a fire burning in the background or something, and Ulrich, was unflappable. Ulrich passed away a few years ago, but kind of set the tone of the group. There was plenty of beer drinking. There were canoe trips on the Sudbury River. And that's kind of where I got to know Yoshi. An early memory is in a bar called the Cambridge Brewing Company. I said something good about the Beatles. Yoshi allowed strongly that there was a band called Blur that was much better, and I recall that ending in a fist fight and us getting thrown out. The other thing that I'll come back to later was I started hearing about the Crystal Palace Football Club. Anyway, so Yoshi, after a couple of years at MIT, went to CERN, where the picture of LEP that he showed was, and worked with the MIT group there, and I commuted back and forth. And what he was doing, he alluded to, was he was actually studying a heavier version of the photon. And a quirk of the standard model is that these heavy light particles, heavy pure particles that are associated with electromagnetic radiation, can actually interact with each other, and photons cannot. And this was the very interesting thing at the time, and this was called, triple couplings. And so I was very interested in that, and Yoshi was doing a lot of work analyzing the data to understand this. And we had to run this big experiment, and at the time, this was well before the World Wide Web, or I guess just as the web was getting started. CERN was this place that had the social dynamics of a large American high school. So there was just lots of going on, lots of young people who were not supervised adequately. And an early memory from those times is Tomi Anticic, who was a friend of Yoshi's, somehow were taking photographs of each meal they were eating or each dinner and posting them online and having some competition about something. I never understood it. And in amongst all of that, we had to operate the experiment, and Yoshi had his red BMW, which came to a bad end one day. I believe it was Yoshi called me in the L3 control room, I think, and said he had been in an accident and his BMW was totaled. And he said, I said, "Oh my God, are you okay?" And he goes, "I'm fine, but my car's totaled." And I think, but he got a settlement from that and bought an enormous gold Mercedes, which I think was the car between the red BMW and the, what was that, a 1966 Comet convertible that he had in California. So after some years at CERN, it came that time for him to write a thesis, which was very, very late, and I was getting antsy, and we were having meetings in the Starbucks once about, why haven't you done your thesis? And Yoshi just said, well, it's not ready. And I said, but I'd like to see a draft, make sure you're on the right track, talk about organization. And it just kept going and going and going. And I was getting more and more anxious because there was a fixed date for his defense. And finally, he delivered it. And astoundingly, it was like almost a final draft. The punctuation was, well, punctuation's better than mine. But the other astounding thing is that the text was 34 pages long. The entire thesis was 52 pages, and it was just a miracle of conciseness. Chapter 6, which was conclusions, is less than a single page, and even that was a fight. So he had measured this triple interaction that I had told about. That was kind of a discovery. And his statement was, the coupling values measured here show good consistency with the values predicted by the standard model, including the triple gauge boson interactions, indicating the triple gauge boson interactions are consistent with their description of those bosons in a gauge theory. And I said, well, that's fine. Don't you want to say something else about this being a first discovery or the importance of this in the larger context? And he looked quietly at me and finally said, no, I think that says it all. And that's fine. I hope, Yoshi, you have stuck to the principle of the short to the point thesis. I was very excited when he went to work on Camland. That was a dream of my advisor, Felix Bohm, a kiloton neutrino detector. it was quite remarkable. An experiment that I worked on with Felix that was 50 meters from a reactor and weighed a ton, couldn't get the job done. And Yoshi and his bunch measured neutrinos at a distance of 180 kilometers, which is why the detector had to be so large. A regret I had was that I kind of lost track of Yoshi around that time, and I never got to see him and Stuart Friedman together, which I think would have been a treat. I'm just going to conclude because I don't want to go on too much longer, like, you know, the drunk uncle at a wedding. I was on sabbatical in Oxford in 2005, and Yoshi took me to a Crystal Palace game. And this was after years of hearing from him. It just was absolutely scathing Yoshi tone of voice, the deficiencies of American football, which is, quote, nothing but a bunch of large men standing around in tight pants, patting each other on the bottom. Americans had no passion for sports. And so he being a season ticket holder to Crystal Palace took me to a game, and we had a great time. And, you know, he was absolutely right. For those of you who haven't been to a football game, there's nothing there except the players, the pitch, some goals. There's not a scoreboard. There are no cheerleaders. There's no jumbotron. But the passion exhibited by the fans far exceeds anything I've seen since. And thank you. That was really an education for me, and I haven't thought about sports since. Since then, he's gone on. He's always working on the absolutely key things. The T2K experiment is magnificent. I hope it runs forever and nails down the matter-antimatter difference that he mentioned. And I just want to conclude by wishing, with something that happened last week. A student who wanted to work with me came to see me, and since stepping down as department head, I've accumulated a bunch of titles, and I'm in the wonderful position in the university where nobody really knows what I'm supposed to be doing. And a graduate student came to see me and asked about working on a project, and we were chatting, and I said, well, what are you interested in? And he goes, well, I'm just interested to meet you because everybody says you just spend your time doing whatever you want to do. And I think the thing I can say about Yoshi is he's spent 25 years doing that in the field of neutrino physics, and with great effect. And my final mark is, Yoshi, you mentioned the breakthrough prize a number of times. There's another prize that you can get that you might want to think about. And with that, I'll call on the assembled audience to give a vote of thanks to Professor Yoshi Uchida.
Peter, thank you so much. We're sorry you can't join us for drinks just outside. So, Yoshi, that was really great. Thank you so much. And we're going to convene upstairs, and there are going to be some drinks and some snacks. And I'm sure Yoshi's very keen, or maybe vaguely keen, to answer more questions. But I think if he has a glass of wine in his hands, he'll be very keen. So thank you so much for joining us.
That's the way.